So far we've been graphing the basic trig functions sine and cosine, and then we did some modeling and writing equations of sine and cosine functions. We haven't talked about how to graph tangent yet, so we're going to do that today, and we're also going to talk about some of the reciprocal functions, secant, cosecant, and cotangent. So, at the beginning of our notes, and I don't think this matches your notes exactly, but this is a nice visual. We have to remember that the recipe for tangent is the sine value over the cosine value. So, essentially it's going to be the slope of that particular radian measure. We're going to come back and look at the unit circle in a moment. But what happens is we're going to take those slopes of all those triangles that we would have had on the unit circle and then graph the ordered pairs, and you're going to see the tangent function develop. Let's take a look at... Maybe not. I guess we're not going to do this. Oh, you know what? We already did this on the other lesson, didn't we? We talked about tangent being the slope of that triangle. So what we're going to do is we're going to look at this screen, and we're going to see that this is a good example of what the tangent function would look like. It's not been phase shifted or anything. We'll talk in a moment about the fact that there is no amplitude associated with the tangent function. So if there's a number in front, it does affect the way the graph looks, but we don't call it an amplitude because it grows without bound. So there is several discontinuities in tangent, because if you think about the ratio for tangent, sine over cosine, in a fraction we can't divide by 0, so any time that the cosine function comes out to 0, which there's several places on the unit circle, it's going to have an asymptote, a vertical asymptote, a discontinuity. And the other thing you might want to notice here is that the period length for tangent is not 2 pi like the other functions we've talked about. The period length for tangent is pi. So that's how long it takes for the cycle to repeat. Now, this non-shifted tangent function, we talked about this on the other lesson when we developed the unit circle. At 0 radians, you think about our unit circle here. This is the ordered pair 1, 0. So if tangent is sine over cosine, that would be the fraction 0 over 1. So at 0 radians, it comes out to a fraction of 0 over 1, which is 0. So if you sometimes forget, like, oh man, I can't remember if tangent goes through the origin or if it goes through somewhere else, just do a quick little unit circle check. And if you have your calculator, of course, you can type some stuff in your calculator. But the idea is the tangent function grows and then approaches this vertical asymptote here at pi over 2, and then backwards it approaches this vertical asymptote at negative pi over 2, and that's the shape of our tangent function. The period length is pi. We don't discuss any amplitudes for tangent, so it's kind of a trick question if I say something like, what's the amplitude? And then for our formula for developing tangent functions, looks very similar to what we did for sine and cosine. The only major difference is this guy right here. The period length is pi over b. So this b that we're going to, again, I always like to have it factored out, you know. I don't like this other form. I like that form. A value is not considered the amplitude. We'll talk more about that in a moment. And then plus, well, you can say plus k on the end here. I think the ones we do are going to be pretty basic, so we'll find out in a moment. The term amplitude does not apply to tangent or cotangent because their heights are infinite. They grow without bound. Okay. Sine, cosine, and tangent are the main 3 trig functions that we discuss often. So here's their graphs side by side by side. So some major differences. They all have domain unrestricted. Sine and cosine have range of -1 to 1. It's a standard cosine and sine function. Sine is odd because it has symmetry of the origin. Cosine is even, has symmetry of the y-axis. And if you look at tangent, there is an infinite range, but the symmetry is with the origin again, so it's another odd function. So major differences right here. Period of 2 pi for sine and cosine, but period of 1 pi for tangent. And then my screen's in the way here, but it does say that the amplitude is not defined in the tangent function. So it'd be a trick question if I ask you for amplitude. If we're going to be using our calculator, make sure that you are in radian mode, because we're going to be graphing in radians. And then don't be afraid to use the zoom trig feature, but especially for tangent, can't really set up your range effectively for tangent, so keep that in mind. Okay, so this section, they want us to find the new period for each trig function, so you just have to be careful which trig function we're looking at. So here the b value is 3, So the period is 2 pi over b, which in our case would be 2 pi over 3. This is cosine, so his formula would be 2 pi over b again, so 2 pi over 5. But here you have tangent. So the period for tangent is normally pi, but then if we divide it by the b value, it's 3. And then here again tangent, so pi divided by 4. So just keep that in mind. Alright, let's get to graphing. So normally I start with drawing the amplitude lines in, but remember for tangent, there is no such thing as amplitude lines. So we just don't draw those. What I'm going to do first is actually calculate the period, which we know is pi over b, which in this case is a 4. So that means the tangent curve is going to stretch a distance of pi over 4, but remember how tangent goes through the origin? And then normally it went pi over 2 in each direction because it splits the period in half through the origin. Well, here, what's going to happen is this first vertical asymptote, in theory I should be able to draw, instead of being at pi over 2, it's going to have to split the period of pi over 4 in half. So pi over 4 cut in half is pi over 8. So this would be negative pi over 8. So in theory I should be counting off by pi's over 8s. The next vertical asymptote would be here. And then here. So 1 pi over 8, this is 2 pi over 8, which you can say 2 pi over 8, or I'm going to reduce it to pi over 4. 1 pi over 8, 2 pi over 8, 3 pi over 8. And then this is negative pi over 8, this is negative pi over 4, negative 3 pi over 8. So if there's no phase shifting, it's really symmetrical, and that's nice. And then you have to just remember the shape of tangent. Of course you can use your calculator if you need a little assistance, but nailed it. Good job, Abruzzo. The next place that we're going to see an x-intercept would be right here at pi over 4. And then we're going to have that supposed same symmetry, but since I didn't draw it symmetrical with the lines. And then here's the next x-intercept. Oh man, so ugly. One of these days, guys. Alright, so that was supposed to look really repetitive and like the same curve every time, but... Oh! Jeepers creepers. Anyone notice what I totally forgot? You probably already did, and you probably already stopped watching my video. There was a reflection. You know what? This is good news. This gives me a chance to do a better job at drawing, right? So that's still negative pi over 4. Because there is a reflection, which apparently I totally disregarded, the curve is not going to go in the same direction. It's going to go like this. Okay, that didn't work out any better. So, bad news. Okay, apparently drawing backwards tangent functions is not my forte. Oh, man. Alright, so, apologies, my bad. Very, very, very bad. Alright, so here... what we have here on the screen is we have a vertical shift for our tangent function. So what used to be the x-axis is going to be shifted at negative 5. So that's one thing I will be marking down. This is not a good start to my day. Alright, so a lot of kids would say, oh, the amplitude is a negative 2 in front of the tangent function. So one thing I'm going to note here is that it's been reflected again, so let's not mess that up. The 2 is going to be kind of like a vertical stretch, but we're not going to call it the amplitude. And I think what these little screens are trying to demonstrate for you is the difference between just like having a regular tangent versus having 2 tangent. So you can see them both graphed here at the same time, where it does go up at a faster rate. We just don't call that the amplitude. It's very hard for us to signify what that looks like by hand. So especially since your teacher can't draw like at all. So keep that in mind. Alright, so here we have 0 radians. The period is just going to be our regular pi because the b value is 1, which means for our tangent function it is going to cross the new intercept here at negative 5 at 0 radians, but it's going to have half the period to the left and half the period to the right. So, so bad. And it's been reflected. I'm not going to forget this time. It's very, very hard for even a good drawer to show that this is growing faster. approaching the asymptotes a little fast. That's not a good way of saying it. It's got a vertical stretch of 2. It's very hard for people to show that by hand. So I'm not going to really mark you down if I feel like you didn't have it vertically stretched enough. So don't panic, especially since I can't draw. I didn't label any of these though. This was negative pi over 2, and this was pi over 2. If we draw one more cycle of tangent, we're going to have another intercept here, the midline, and then have another, wow, it's not even close to vertical. Alright, so counting by pi's over 2's, this guy here would be 2 pi over 2, which is pi, and then this guy here would be 3 pi over 2. Again, it's been reflected, don't forget that part. So bad. I don't know if this is my drawing day. This is not boding well. It's like, oh, not even 8 in the morning, and I can't draw. Alright, so that's enough struggling with tangent for your teacher. Let's talk about graphing the cosecant function. So the cosecant function is the reciprocal function to sine. So what we have on our paper here is a rudimentary sine graph, a regular sine graph, nothing fancy happened to it, that's been kind of sketched in. So if you think about reciprocal fractions and what that means for our output, anytime we had a 0, so that means the fraction was probably like 0 over 1 from the unit circle. Well, if you take the reciprocal of that, you end up with 1 over 0, which is an undefined expression. So if I think about translating that to a graph, anytime I used to have a 0, it's now going to become an undefined value for the function, which means it's going to be a vertical asymptote. So basically what I'm going to do is I'm going to take every time there's an x-intercept of 0, or an x-intercept, I'm going to draw a vertical asymptote through it. Stellar job as always. You know, my graphing skills are really bad today. I'm feeling really sensitive about it. Alright. So the other thing I want to say about coming up with the rest of this function is what we would do normally is we would take the ordered pair and we would give the reciprocal output to it. So what we end up with is a shape that ends up looking like a horseshoe, is what most kids signify this as. So this ordered pair here, these are going to match because this is, you take the reciprocal of 1 and it's still going to be a 1. But the other points are going to end up going like this. Oh gosh, so bad. So ugly. Okay. And then again here, if you take the reciprocal of negative 1, it's just going to be negative 1 again. So here. Oh god, it's getting worse. Alright, and then again here, that's the only point they match up at. Ah, jeez. These are all supposed to be the same size and shape. I'm just doing a really bad job. This is, maybe I should just go home. This is not going to be my day. Alright, so that's what cosecant looks like. Even to this day, guys, of doing this for so many years, I don't usually like look at a cosecant graph and think right off the bat like, oh my gosh, it's cosecant. I know it's either cosecant or secant because of the horseshoe shape, but I really have to kind of think about like, okay, who would we match up with? Which reciprocal function would it match up with? So I always, this is what it was supposed to look like. I always graph his reciprocal original function, like really sketch it in like a ghost function, and then I play off of that. So some attributes, the range is kind of weird because there's a whole like undefined part where the actual sine function was, but it splits off above that range. The domain is all reals except for the multiples of, I think there's some sort of a typo on your page. It's the multiples of pi, because that's where the fraction would end up being undefined. And then it still has a period of 2 pi. It is still an odd function. So it has a lot of similarities to his reciprocal buddy, the sine function. Now let's talk about secant. Secant is the reciprocal to cosine. So we have a little ghost cosine function graphed here. And the same thing is going to happen that we saw with cosecant. Anytime I had an x-intercept, that's going to turn into a vertical asymptote because it'll be undefined. So we end up with this. You know, I'd like to blame this on the fact that I'm on a tablet, but I don't really know if that's fair. I don't know why this didn't connect all the way, but whatever. Pretend. Alright. I think I misjudged that last one. That's okay. Alright, so same idea. If I took the output reciprocal of 1 from the unit circle, it becomes 1 over 1, so it's still a 1. So we're going to match up here for secant. And we end up with another horseshoe. Same thing here. Negative 1's going to match up. And then we have a horseshoe. Jeez, these are looking bad. Horseshoe. And then... so bad. Okay, you know what? I'm just going to give up. So on the next screen, I bet they give us... See, there's a pretty one. Alright, so this is what it's supposed to look like. Not at all what I drew. The domain is all reals except for where those vertical asymptotes show up. So all the multiples of pi over 2. Odd multiples of pi over 2. Because 2 pi over 2 would be 1 pi, and there's no asymptote there. Same issue with the range. There's like its undefined piece in the middle, but then the range goes up and down forever off of 1 and negative 1. Period is still 2 pi, and then just like cosine, also an even function. Alright, so here we have the cotangent function. It's going to be a reciprocal of tangent. Same issues as the other reciprocal functions. Any x-intercepts will turn into asymptotes. And any asymptotes will turn into x-intercepts. So, like here, there was a vertical asymptote, but on my new function, that's going to become an x-intercept. Same thing here. Oh boy. Getting bad. And then in these x-intercepts are now going to be asymptotes. I'm really nervous to craft this one. You saw how my other tangent functions were going. I can't believe cotangent will be any better. Alright. So if I think about what the shape would end up looking like, the shape of the tangent function is going to kind of reflect because the reciprocal component to it. So this is going to be the x-intercept. But instead of growing like this, like a tangent function would, cotangent actually does this. Oh, God. So bad. Alright. Oh, gosh. This is not... The good news is for most of my classes today, I don't have to draw anything. It's about the only good news I have for myself today this morning. Ugh. Alright, let's see what it was supposed to look like. Next screen. There you go. So, same idea. It's got a lot of commonalities with tangent. Some major differences, though, are where the asymptotes occur. It's still an odd function, still a period of pi. The range goes on forever, just like tangent did. But the domain are all the numbers except for the multiples of pi, because every time... I didn't label anything. Oops. Anytime we hit a multiple of pi, we add a vertical asymptote, because those were the x-intercepts for the original tangent function. Goodness gracious. Alright. So this next question. They want me to locate the vertical asymptotes and sketch 2 secant 3x. So what I'm going to need to do, because this is how I need to do it, I need to graph his buddy to cosine 3x as like a ghost function, and then we'll draw the horseshoes and the asymptotes off of that. So if you're better than me and you don't have to do all that work, that's awesome, but I'm not that good. Alright, good news is there's no phase shifting here, so this is 0. If I think about the period length is going to be 2 pi over 3, because the b value is 3. And if I think about quartering off that period, 2 pi over 3 cut into quarters, so think about, dividing by 4 here. That would be a pi over 6. Oops, I said 6 is my quarter point. So, I'm just going to count off by 1 pi over 6, because frankly, guys, I'm just not having a good day. So this is 1 pi over 6. This is 2 pi over 6, which I know reduces. This is 3 pi over 6, I know that reduces. And this is 4 pi over 6. I screwed up. Oh, I didn't. Did I? No, we're good, because that's 2 pi over 3, and that's the period. Okay, gosh. Alright, so let's count backwards. Negative pi over 6, negative 2 pi over 6, negative 3 pi over 6, and negative 4 pi over 6. So I'm going to ghost in the cosine function. Oh, but I haven't drawn the amplitude lines in yet. So, oh, jeez. Can't even ghost in a horizontal line today. Gosh be golly. Alright, so this is 2, this is 0, this is negative 2. Now I'm going to ghost in the cosine function, which I know should start at the top, the max line, put them in, back to mid, back to max. So it's going to look something like this. And then come back here. You know, I was about to say I was ghosting in pretty well, and then the minute I went to go say it, I screwed up. Alright, there we go. So that's not the function I want. I want his reciprocal function. So what I'm going to do is every time it hit the x-axis, I'm going to draw in a vertical asymptote because the 0 is going to turn into an undefined expression. So we have a vertical asymptote here, vertical asymptote here, vertical asymptote here, and here. And actually, that was the hardest part of the whole graph, was getting the ghost function put in and then the vertical asymptotes. So now, remember the time it hits the amplitude lines, they're going to match up, and everything else is going to be one of those horseshoe pieces. Gosh. You ever just feel like giving up, guys? I'm there. Whew. That is not symmetrical, but you know, sorry. Let's try this one. We're just graphing regular tangent here. The b value is a 4 pi, which is kind of unusual. So normally the period's pi. If I divide that by 4 pi, I end up with a period length of 1/4. So again, it looks like the amplitude is 3, but there's no amplitude for tangent. So I don't need to mark in any max and min lines. It just means it's been vertically stretched. So when I do graph this, I'm going to try to make it appear vertically stretched. But remember, the period is 1/4. So that means starting at the origin for tangent, remember starts at the origin, it's going to have to stretch symmetrically, if there's no phase shift, half of the period in each direction. So this would be 1/8 and this is -1/8. So those would be the locations of the vertical asymptotes. Gosh. Ready? I don't have good feelings about this. Gosh. Okay. Alright, and then symmetrically placed, let's draw one more cycle, and then I'm going to call it a day on this one because I don't want to press my luck. So bad. Alright. I'm sure it wants me to graph more, but I just can't, guys. I just can't. There we go. Alright, let's try cosecant. So we're going to sketch in the ghost function, which would be 3 sine of 2x. The period is 2 pi over b, which is 2 pi over 2, so the period's pi, which means when I go to graph my quarter points, I'm going to quarter up that period and count by pi over 4s. Good news is I haven't given you any of the phase shifts, and if I look ahead in my paper, I don't think I ever do give you any with phase shifts, so that is excellent. Alright, so amplitude this time we do need to mark amplitude lines, because that's going to be the beginning of the horseshoe. I'm not using technical terms here, clearly. Oh gosh. Man, it's just getting better and better. Alright, 3, 0, -3. And then we decided the quarter points were pi over 4s. So here, and then 1, 2, 3, 4. Go backwards. 1, 2, 3, 4. So 1 pi over 4. For the sake of my brain, I'm just going to leave them as 2 pi over 4, 3 pi over 4, and 4 pi over 4. But yes, some of those can reduce. The 4 pi over 4 and 2 pi over 4 will reduce if you're doing this for a test, but I'm not. Alright, so sine, the ghost function for sine, remember, we're not actually graphing sine. Backwards. Alright, ghosting it in. And for a lot of kids, they don't even have to draw this part. They can just draw the x-intercepts, and then they go and draw the vertical asymptotes after that. I'm not one of those people. Obviously, I need all the help I can get when it comes to graphing. Alright, so these x-intercepts become vertical asymptotes for undefined reciprocals. Go on here, go on here, go on here, Okay, now we're going to graph in our horseshoes. They have that matching point, but everything else goes like that. So bad. I apologize. This is why they don't let me teach geometry, because, you know what, geometry doesn't get any better drawings than this does. There we go. Alright, so if you can notice, the period length is still pi. All those attributes that we know for the reciprocal functions are still kicking in there, so yay. Oh, this is going to really challenge me. It's got a reflection, it's a tangent. It's got a period change as well. I'm going to look ahead in our notes here and see if there's a different function that I'd like to talk about. So we'll do this one. Alright. The period is supposed to be pi divided by b, so pi divided by half ends up being 2 pi. But remember, what happens with tangent is it goes through the origin, and then half the period is split among, along the origin there. So 2 pi cut in half would be pi in each direction. So those are going to be our vertical asymptotes. Gosh. I need like a lesson. Now, Bruzo, do not forget, there's been a reflection. So it's not the regular tangent shape, it's been reflected. Ah, showed such promise there at the beginning, huh? Alright, I'm just drawing the one cycle, guys. I can't do this. Alright, cotangent 2 pi, 2x. It's not very exciting. We better do it. I don't think we've done the cotangent yet. So the period length is supposed to be pi, but it's got a b value of 2, so the period is now pi over 2. Now remember, cotangent does not go through the origin. Cotangent actually has a vertical asymptote at the origin. Whoops. And then what I usually do is I count off 2 tick marks, and the second one is going to be my next vertical asymptote, because this is the entire length of the period. So I do need to do some labeling here. The period is supposed to be pi over 2, which means this halfway point is going to be pi over 4. And then I have to remember what cotangent is supposed to look like. Cotangent looks like that. So, my arch nemesis, that shape is just, oh, you know what? I'm going to call that a win. I thought that was pretty good. Alright. I'm just drawing the one cycle. I'm sure you guys can count. Oh boy, let's talk about this one. We have a vertical shift of up 3. And that is important to note because the midline of the ghost function that we're going to be graphing is an important feature. And then we're going to be ghosting in a sine x plus 3. So the sine function, normal period of 2 pi, because it doesn't have a b value other than 1. And then the quarter points would be counting off by pi's over 2. 2 pi cut into quarters is pi over 2. So, the amplitude is a 1. I'm going to draw in the max and midline then, so going up 1 unit, going down 1 unit. Oh gosh. Oh, it's looking so bad. Alright, I'm going to ghost in green this time because I'm having a lot of trouble seeing what I even have drawn here. Sine function, remember, starts at the midline. And then if I think about what we're counting by here, it looks like we are counting by pi's over 2 because this is 3 pi over 2 in. So the next tick mark is my max. Back to mid, back to min, and then this must be 2 pi here. So here we go. And then that's enough to get me going on the pattern. To go backwards, and then again, this is not even the function I want. This is the ghost of the reciprocal function. It's very ominous, isn't it? Okay. So what would have been the x-intercepts, which I know is actually not an x-intercept anymore, it's the midline intercept. This is one of them, so it's now a vertical asymptote, and so is that, and so is that, and so is that, and that one. There we go. Alright, so now at the top of the amplitude lines here, and the bottom of the amplitude lines, that's where they're going to match up, and then I'm going to kind of sketch in these horseshoe shapes. So I know, not the technical terms for what these are, it's how I remember them. Missed it. Big dot. Okay. Alright, I think we're going to stick a fork in this lesson because I am done. Sorry about the rough graphing, but you get the idea about the reciprocal functions. If you want to look into more of how they developed, you can go back to the unit circle and think about all those ordered pairs that we plotted, and then plotting the reciprocals for the output. However, sometimes it's just worth memorizing the shapes, so this might be one of those cases. All right, good luck.